Welcome to Lesson 5 of Applied Physics. This lesson covers forces and Newton's laws. In this lesson, you will cover the following objectives. Be able to state in words Newton's three laws of motion. Understand the difference between mass and weight. Be able to define the term force. Be able to state what is meant by the term free body diagram or FBD. Be able to construct FBDs and use them to aid in solving problems. Be able to apply Newton's laws of motions in a systematic way to solve problems. And be able to state what is meant by the term normal force and incorporate this definition in solving problems. Sir Isaac Newton was an English mathematician, physicist, astronomer, alchemist, and natural philosopher who is generally regarded as one of the greatest scientists and mathematicians in history. Newton wrote the Philosophiae Naturalis Principia Mathematica, in which he described universal gravitation and the three laws of motion, laying the groundwork for classical mechanics. By deriving Kepler's laws of planetary motion from this system, he was the first to show that the motion of objects on Earth and of celestial bodies are governed by the same set of natural laws, was integral to the scientific revolution and the advancement of heliocentrism. Among other scientific discoveries, Newton realized that the spectrum of colors observed when white light passes through a prism is inherent in the white light and not added by the prism, as Roger Bacon had claimed in the 13th century, and notably argued that light is composed of particles. He also developed a law of cooling, describing the rate of cooling of objects when exposed to air. He enunciated the principles of conservation of momentum and angular momentum. Finally, he studied the speed of sound in air and voiced a theory of the origin of stars. Despite this renown in mainstream science, Newton actually spent more time working on alchemy than physics, writing considerably more papers on the former than the latter. Newton played a major role in the development of calculus, sharing credit with Gottfried Leibniz. He also made contributions to other areas of mathematics, for example, the generalized binomial theorem. Mathematician and mathematical physicist Joseph Louis Lagrange said that Newton was the greatest genius that ever existed and the most fortunate, for we cannot find more than once a system of the world to establish. Up to this point in the term, we have analyzed motion, described, without worrying about what was causing the motion to occur. We said that such a study of motion was referred to as kinematics. We now concern ourselves with why the object is accelerating or not. In other words, we look for the cause of the motion. This type of study of motion where the cause of motion is considered is called dynamics. Central to this discussion are a set of laws called Newton's laws of motion. This set of laws is considered to be of fundamental importance to the study of classical mechanics. Once introduced, you should be able to state these laws and apply them correctly, even if stirred from a deep restful sleep at 2 o'clock in the morning. These three basic laws are stated as the law of inertia, the law of unbalanced forces causing acceleration, and the law of interactions between bodies. In the pages that follow, there are words that are highlighted in the statements of Newton's three laws of motion. This highlighting is to indicate that these words are critical to the statement of the law, and you should keep them in mind when applying these laws so that difficulties can be avoided. We begin with Newton's first law of motion, the law of inertia. Which sumo wrestler in this image has more of it? Newton's first law of motion states, an object in motion with a constant velocity will remain in motion with that constant velocity until the object is acted upon by a net external force. This law is also called the law of inertia. Inertia is the property of an object to resist a change in velocity. Mass is a quantification of the inertia of a body. The figure shows a classic inertia demonstration. If you flick the card straight off the cup, the coin will fall downward because of its inertia. The coin is a body at rest with balanced forces acting upon it. Once the card is removed, The balancing force called the normal force no longer exists, and the force of gravity, which is pulling downward on the card, is unbalanced, and an acceleration occurs toward the bottom of the cup and the unbalanced force direction. Hence, the reaction to the unbalanced force is a non-inertial state called acceleration. Now, take a few minutes and click on this link to see an interesting application of inertia with a brief study of the Olympic sport of curling. Take a look at this jet airplane. Think about all the different forces acting upon it when it flies through the air. The jet airplane has a number of forces associated with it. You can easily see from this free body diagram that the forces on the airplane are balanced. Balanced forces cause what? The answer to that question is constant velocity motion, an inertial state that is non-accelerated. The statement of this law raises a question. What do you think will happen to the motion of the object if there is an unbalanced outside force? Answer: the object will accelerate. Again, balanced forces cause what? Balanced forces cause an inertial state of motion called constant velocity. It's good to have this kind of state of motion when you want an object to be at rest or moving with the same constant speed. Unbalanced forces cause an acceleration. There are two basic inertial states, rest and constant velocity. If you are not in one of these states of motion, you must be accelerating. Isaac Newton's ideas from statics and dynamics came from three initially stated laws. The first one was the law of inertia. An object in motion with constant velocity will continue with the same constant velocity unless acted upon by an unbalanced outside force, and an object at rest will continue at rest unless acted upon by an unbalanced outside force. This lesson describes the importance of understanding whether or not an object is in one of these states. If not, it is in a non-inertial state known as acceleration. This means you will have to think about and apply Newton's second law of motion to that type of situation. A useful tool to determine whether or not forces are balanced is the free body diagram. You draw the forces that are acting specifically on one isolated body and then ask the question, are the forces balanced? If so, then the object will be at equilibrium and will exhibit the properties of inertia. If not, the object will be in an accelerated state, and Newton's second law will have to be applied to analyze the rate of acceleration. An excellent example of drawing free body diagrams can be found at the website called The Physics Classroom. You should visit this site and learn the basics of free body diagram drawing. We will then describe the instructor's basic method for drawing the same type of diagram in the next series of pages. The methods of drawing a good free body diagram will be discussed here. The first three steps in constructing a model are: identify the object or system, identify the forces acting on the object or system, and draw a force or free body diagram assuming the object or system as a point particle. Another good site to learn how to draw free body diagrams is located here. Go to the website and watch the slides, and when you return to this lesson, you should be able to draw free body diagrams as described in the following pages. An additional warning. One cardinal rule is that once you identify the object, it cannot be changed unless you start all over with step 1 again and go through all of the steps with the new object. In order to make a conscious decision to choose the object or system, and to avoid changing it midway through the activity, you will need to draw a rough sketch of the important parts in the situation being investigated. The problem you are given says a man lifts the weights. You should choose to draw a man with weights lifted overhead. Circle the weights because the question wants to know what forces are acting on the weights. Isolate the system before you start. You will only worry about the object of interest and the forces acting on that object. What forces act on the weights? This is the real-world representation. At first, the sketch will be provided for you, but later in the laboratory and in word problems, you will need to complete the sketches on your own. The forces that need to be identified are those forces acting on the object or system. Each of these forces has to be caused by an object outside of the dotted line circle. It is important to identify the agents outside the object or system that are exerting forces on the system. This is just a casual reminder to remember the following about units. A free body diagram assumes that you are looking at forces and the units of force are the Newton or the pound. A free body diagram or isolated body diagram is useful in problems involving equilibrium of forces. You should remember to use the units of force. Don't assume that information given in a problem is correct with correct units. Also remember that free body diagrams are useful for setting up standard mechanics problems. Here's a sketch of another example of a free body diagram which shows a force pushing an object to the right with a frictional force opposing its motion directed to the left. What is true if the forces are balanced? Answer: the object is at rest or the object is in constant velocity motion. Weight and mass are not the same. Mass is an inherent quantity that all objects have. It is measured in kilograms. In this lesson, we only need to deal with the weight vector. The direction of the gravitational force is always toward the center of the Earth. A free body diagram is a sketch of an object of interest with all the surrounding objects stripped away and all of the forces acting on the body shown. The drawing of a free body diagram is an important step in the solving of mechanics problems, since it helps to visualize all the forces acting on a single object. The net external force acting on the object must be obtained in order to apply Newton's second law to the motion of the object. Reviewing information about forces, there are two basic categories of forces to consider: contact forces and forces at a distance. As you can see, weight force is a force acting at a distance, and the other forces described are all because of a direct contact. Forces at a distance arise when the object is in the field caused by another object but not in contact with the object. Examples of fields are electrical, magnetic, and gravitational fields. Since we are only dealing with mechanics in this lesson, the only force at a distance we will deal with is the gravitational force. Gravitational force is often called weight. To show the force in this image, we would place the tail of an arrow at the center of the object. We label this force with the symbol W and the statement "force caused by Earth." This is an example of a force acting over a distance. Magnetic and electrostatic forces are also an example of this, but won't be studied during this applied physics course. You will probably only need to consider the weight as a force acting over a distance in this lesson.